All right, hello everyone. It's January 18th again. It's earlier today, so I didn't do much today. Mainly, I studied extreme gradient boost tree. I've heard good things about it. I saw some questions on Stack Overflow about hyperparameter tuning using the XGB ranker, but that's a side story. But the main thing is, I know I've read some article that says, if you're doing machine learning, or like if you're not in the research setting, trying to push the new algorithm or whatnot in a regular company, and you need to do, say, classification, and you're a machine learning or data scientist or whatever your job is, and your job is to turn data into some insights. And there is only one classifier. I'm not sure about the regressor, but for classification, for sure, there's only one that's the best. So you don't even have to argue. It's gradient boost tree. And of course, you can use this extreme gradient boost tree. So I was just trying, because in my project, I use support vector machine. And this is always my favorite because I've learned the basics about support vector machine, mathematically speaking. If you can use support vector machine, you should use it. It has really, its performance is mathematically speaking is guaranteed. However, the good things about extreme gradient boost just kind of, I want to try, and I tried it. I haven't done a full analysis on it compared to the SVC based classifiers, but just from one example, it's like, I won't say very good, like just blowing away what SVC can do, but it does have some interesting results that I really like to explore further. Yeah, how about we just put it that way? And the implementation of that XGB tree is really fast. So I was able to do some serious hyperparameter tuning on it, and it looks actually quite solid. So tomorrow, I will definitely do it systematically because I have a lot of classifier to tune, and I'll tune all of them. And once I'm done tuning all of them, I can start to, understand how good it actually is, you know. So yeah, so that's that, and let's get into today's challenge. So we have this problem we haven't fully. This solution is terrible, and the solution I didn't read it, but I saw this prefix and suffix sum, so I want to try. I thought about it yesterday, and I know what it means because for this one we want to find the maximum subarray sum, right? So we go on, so we know all of this. Then the only possibility is a crossing, right? So we put this to the end of itself, so we need to know what's the maximum crossing subarray. So that's the question. We want to find the maximum crossing subarray. And the hint that I saw was a prefix sum, right? The prefix sum could be at the end, the suffix sum could be at the front. And then I was thinking, okay, so in order to make it like a big, we need for them to be monotonic increasing for the right side and monotonically decreasing on the left hand side. So I said, yeah, we can definitely do that. So I can do monotonic increasing like from left to right on the right side and then right to the left side. And then I'll have everything just getting bigger and bigger on this side and getting bigger on this side. Then we have to take the first two, right? Then it could be just decision. We should always try to take more, right? But when we take more, we should also take in consideration that we might run it outside the length. So I was thinking, okay, on the two sides, we can compare the values, right? We definitely want a bigger value, so we can try the bigger value. But also we need to be worried about the length. So I haven't figured out like a full solution for this, Like, I don't know how to iterate in order to get it to work. I mean, what we can do is, we can iterate over. Yeah, I don't think iterate over is the way to go, because the runtime we saw is on. Runtime is on. I mean, we can go see how far we can go, and then what? Actually, I don't know. I was going to say we pick the largest, right? And then we have a new start. Then we pick the next largest. But if this one side is larger than this, then it's got to be this side. But it could happen that if I get multiple here. So, I actually don't know. You know what? Let's not waste time. We're going to take a look at the solution for this one. It's pretty tough. And we also have to deal with this one. Yeah. Unfortunately. I mean, I'm going to reanalyze it. I mean, the thing is, the error case is just so bizarre. Like, so giant values. I really can't do anything about it. Like, I want to analyze, but how am I supposed to analyze? What the hell? You look at this, is right? You're like, what the hell? I mean, I don't know. We're past 37, so maybe we can analyze a little bit more and trying to see where we got it wrong. Yeah. So this will see the solution. This I actually want to try again. But anyway, all depending on whether we can solve this one fast. Subarray sums divisible by k. Given, it's all subarray this time, huh? Given an integer array and an integer k, return the number of non-empty subarrays that have the sum divisible by k. Okay, a sum that is divisible by k. What do you think? Well, so the sum is divisible by k. Then each one must be divisible by k. I'm thinking about subarray usually a few options that we can try. Maximum subarray is definitely Cardane. And sliding window, that's one of the ways to deal with subarray if we have like a set size. Another thing that subarray usually do is prefix sum. So I think this problem is prefix sum, because when we do the prefix sum, any sum of a subarray is the difference of two prefix sums. And to make this difference divisible by k, each value has to be divisible by k. Right? So a minus b equals k times something. That means a has to be divisible by k, and then b has to be divisible by k. Because anyone is not divisible by k, this is not happening. Unless we're dealing with 0. 0 is a special case. Okay? If it's not 0, actually, I just take it back. Okay, we can do 9 and 4. 9 and 4 is divisible. No, that's not right. But still, that could be a good start. We do prefix sum, right? We do prefix sum, and then for each one, we can try. If it is divisible by, or put it this way, if the value is divisible by k, then the only value I can do must also be divisible by k. That's right. But it's possible that neither is divisible by k. Oh, it's not divisible by k. It's the, what's that thing I was thinking about? The remainder. They have to have the same remainder. Yes. That's the one. They have to have the same remainder. So we do a prefix sum. We get each one mod k, and we have the remainder. And then we find how many of them have the same. So we run a counter, right? So when we run a counter, if a counter we have more than, if I have 1, now 0 is a special case. 0 is special. We deal with 0 later. If the remainder is not 0, then we can do a combination because any 2 will work, right? So if we have 3 values that have the same, 3 of them have the same remainder, then we can do 1 minus 2, 1 minus 3, or 2 minus 3. So we do a combination. And back to 0, 0 we definitely do combination, but in addition to that, for 0, they are also good on themselves, right? They're also good on themselves. So we have to add themselves as well. Okay, so that is a strategy where you can try it. See, this one feels much easier than yesterday. All right, yesterday was pretty painful. Very painful. Well, I mean, the most painful part about yesterday was I thought it was easy. I thought it just, we cardang it and then we're done. But it's not. All right, we need a counter. We also need, what's that? Accumulate. Okay. So we can say counter equals counter accumulate nums. For a in accumulate nums, we say a mod k. Okay, and then rest equals 0 for kc in counter dot items. Okay, if k is, we can do rest plus equal to int k is equal to 0, right, times c plus math.combination c choose 2 and return rest, which I'm pretty sure I can just do return sum for this. Then we do this. All right, I'm pretty sure I can attach this to here and it becomes a one-liner. Huh. Don't be so confident, man. Might not be right. Oh, we'll see. We'll see if it's right. If it's not right, then we deal with it. Yeah, and also like 0 kind of situation, how you're gonna deal with those. But it doesn't hurt to dream. All right, let's see if it works. It does work. I have confidence in this one. Let's try this. Ooh. Got it. Wow. What was I doing in the past? It's no problem. I'm curious to see. It's October, right? 1 year. Yes. Yes. Counter. Ah. A prefix sum. Ah, we can keep doing this, yes. Every time we see one. That's true. So much smarter this time, huh? Oh, I remember this. I remember this problem. This was I think considered a difficult back then. So what was my other solutions? Yeah, this I know. I don't know what this is. I'd accumulate. I don't know. Wow, so we saw some growth. We saw some growth. Huh. I want to post this. Find, use prefix sum, find each prefix sum's remainder after mod k, then count the frequency of each remainder. For each frequency, we use combination to calculate the total number of substrings. To calculate total number, right? Total number of substring, subarray, combination of subarray possibilities. Number of prefix sum. You know what I'm talking about. The only tricky part is to consider remainder 0 separately, because each individual prefix sum that has 0 remainder counts as a good count towards the results. All right, we call this ugly one-liner. How about this? Just for fun. New. I like to do this. That's what? Combinatorial, right? Combinatorics. Combinatorics. I'm not sure if that's a word. No, that's the science. I want to know the name of combination number. What's it called? Combination. What is it called? Combination. Combination. a combination. One liner for fun. Well, I always try to provide a link. I have to open this. Okay. All right, so yeah, pretty well. All right, let's see. Enumerate prefix, suffix, and then what? Special sum. Increase prefix sum by, well, I need to read this. Or special sum with a maximum of prefix sum and a suffix sum of the other. Yes. Yes. Max sum of a prefix sum and a non-overlapping suffix sum. Enumerate a prefix with its sum and add the maximum suffix sum that starts after the prefix so that the prefix suffix don't overlap. Okay, suffix sum where suffix I represents the suffix service in starts with index I. Yes. Construct an array right max where right max I equals the maximum of these is the largest suffix sum of them that comes at or after I with right max. We can then calculate the special sum by looking at the prefixes. We can easily accumulate the prefix while iterating over the input. And at each index I, we check the right max to find the maximum. Oh. The maximum suffix sum starting at this or towards the end. So we can just go find out that at every single position. And once I find it and I go to prefix sum, right? Then we just do this. Holy moly. Wow. This is good. This is very good. Huh. That does not overlap. DPI records the max suffix sum starting at I or later. Okay, so now what we're gonna do, so we're gonna do Cardane. We can do special sum first. Yeah, I'll cross sum. And we need a suffix sum. Okay, so we need to say dp equals, actually I do need this. So dp equals, I say 0 times n, I in range n minus 1. Okay. Actually, we don't have to do that because we can say dp minus 1 equals nums minus 1. Okay, and I can do from this towards the end, and we say dpi, right, shall equal to suff sum equals nums minus 1. Okay, so suffix sum plus equal to nums I, and dpi should be the maximum of what? dp I plus 1, because this one, this is the maximum, and then we add 1, so it's a suffix sum. Okay, and then we'll keep going, so this will handle the suffix sum, and then a res will equal to, no, not res, then we will go, we'll go once and then we do both. So suffix sum cross max cross equals, okay, so now we say for I in range all the way to, not to the end because I don't want to go to the end. Now we can have prefix sum, so pre sum equals 0. Pre sum equal to 0, right? And then what do? We say pre sum plus equal to nums I, right? And then max cross are equal to maximum, the max cross, pre sum plus dp I plus 1, right? So blah 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 all the way to the end. So now we have max cross, and then we say Cardane will equal to 0, current max equal to 0, right? Oh, okay, so current max equals nums I. Actually, no. Minus math.inf. Actually, this is both minus math.inf. Okay. Build dp. Find a max crossing sum. Use Cardane to find normal max subarray sum. Okay, for n in range, for any nums, a current max shall equal to maximum n n current max plus n cardane equals max cardane current max, and then we return maximum of cardane and a cross max cross. Okay, let's not do this. Solution 2. Let's try all these. Oh, this is so good. This is so good. Yeah, of course, because it's using cardane and everything else is ON. Screw me, huh? Holy guacamole. ON. What should I say? You shouldn't say anything. Alright, we have a solution number 2. Minimum subarray. Oh, this is the second time. This is the second time. I remember another question uses almost exactly the same. To find the subarray with minimum, so the remaining must be maximum. Holy crap. Holy crap. But I think the other one uses sliding window. Yes. If minimum contains, so that's the minimum. So everything is negative. All right. If everything is negative, then it should be the smallest negative. Yeah. Oh, we do have to, because then it will be a 0. Ah. Holy crap. This is brilliant. Main subsum. current min. Current min plus n. Min subsum equals minimum min subsum and current min. Right? Once we finish, then pay attention. Pay attention to the edge case where all nums are negative, in which case the min subarray sum would be the entire array. That would lead to the max cross sum being 0. But in this case, the answer should be the smallest, but be the biggest negative value. Should be a negative value. So we need to check whether the max cross sum is 0, right? Yeah, if it covers the entire thing, and it's a 0. Why would it be a 0? It must be negative. Because it would be negative. If we have some positive, we can not include that positive, right? So it would definitely be a negative, which means the total minus this, right? The total minus this. So we can say total sum, no, max cross sum nums minus min subsum. If max cross equal to 0, return the maximum nums. So this is every number in nums is negative. Yeah, as long as we have one positive, well, we have 0. And what if it's all 0? Yeah, it's all 0 would be this. What if we have some zeros? If we have some zeros, the max cross sum is not a 0. If we have some zeros, then we start adding, and those zeros will be ignored. Like it won't be a small portion, it will be negative, right? So the remainder will not be 0. Oh, the remainder. Yeah, because we sum everything together, right? Even we have some zeros, it's okay. That's my understanding, right? And then we do Cardin, and then we run this. Let's see, 3. Yeah, this is correct, but I think I want to test something with negative values. Yep, let's see. Ooh. Yeah, because I only consider one situation. I need to consider 2 situations, and I didn't understand. 17, but I also get 9. Okay, so what is the maximum? Will be minimum will be this, right? Hold up. My answer is 9. Huh. The whole thing. No way. No way. $17. Yep. Here the same. Let's see. Minus 13, minus 26. This is minus 26. I think the rest just add up to 0. Holy crap, it is. Oh, wow, it is. So it cannot. I have to make sure. I mean, if every number max crosses 0 doesn't mean every number. So we just need to know if every value is negative. Right? How do we tell if every value is negative? I think that's just the edge case, and we don't have to consider this. Yeah. What we shall do is to see if every value is negative. Num negative, negative count, neg count. Do this. Now, if neg count is equal to len nums, return max nums. Whether all numbers are negative. But that should be the only thing we need to check. Otherwise, we'll be fine. Alright, because in all the other cases, we don't care. We did do max cross. The only thing we need to worry about is this negative count. Try it again. It's the only edge case. This one need to go at a nightmare. Took so long and so much effort. Oh, sum equals mean sum. Then we just use max sum. We don't have to. Update. No need to count negative. Just if max cross is 0, we'll always use right? Because if all numbers, if max cross is 0 due to all numbers being negative, we shall use Cardin. If max cross is 0, not because all numbers being negative, right? Then 0 is the max, is indeed the max cross. But that also means there must exist some positive values, some non-negative values, which can be picked up by Cardin. Which means we have mean, mean sub current mean, okay, max subsum, and current max. Why don't we do this? Current max equals maximum n current max plus n, mean and the max subsum, maximum max subsum current max. Say total equals sum nums shall return total is equal to mean subsum, then we just return max subsum, else with the maximum, the max subsum with total minus mean subsum. That is the better solution. Yes. All right, done with this. Now I come to this one. How do we analyze this? Can we create a test case? Yes, we can. We can create a test case. These two don't even have to be the same length. Oh, was it guaranteed? I just put the... Oh, that's the thing. It has this guarantee thing. absolutely hated it because I can't even analyze this. Can we just 1, 2, 3, 4, 5, 6? Can we do that? Please don't be specially created. Well, it's nice. Please be correct again. Nice. Now this is really... that's probably not right. It's unique. That I don't know, man. Not sure about this one. Ugh. This one's correct. Should have copy and pasted the early one. Okay, so we know this one's not correct. Now the goal is to reduce this. I'll remove half. It's correct. And I'll remove the other half. Limit j must consist of values from 0 to... One, 2, 3, 4, 5, 6, 7, 8, 9. What do we have? 4. Oh, at least as long as these add up. Oh, yeah, as long as they add up, they have a solution. Dang it. But yes, as long as they add up. As long as they add up. Hold on. Let's do 100. That'll be interesting. We want robots, right? We do robots, land robot. Let's say land robot, we want to do, how about 5 robots? Seven robots, okay? That's still within capability. And then we just need to have the positions, right? The positions. Position from -10 to 10, okay? From -10 to 10, we need to pick 7. So actually, okay. Well, let's call L equals 7. And then robots shall equal to choice. Is a choice to take, hold on. Oh yeah, what is no repeat? Sample. Yeah, I think example is no repeat. Without replacement, yes. Duh. Sample. Is it raining again? Tell your range. There's a sequence, yeah. Over to L. And then how many this do you want? Let's do 5. Okay. Machine equals 5. And then factory is sample. Oh, it has to be different. I see. No. Okay. Robot equals 7. Robot machine robot factory equals 7 and 5. Okay. And all positions are going to be sample. Range -10. Okay, -20 to 20. R plus F. Okay, that's all the positions. Then we need to randomly choose some values such that their sum is larger or equal to 5. Oh, maybe also be smaller than 7. Okay, with a choice to 7. And for 4 of them. Limbs shall equal to choice from 1 to robot plus 1 how many factory number, while sum limbs is smaller than robot, the total number of robot. Then we do this again. Ah, Jesus. Okay. So once we done, we get the position, we got the limit, then we say robots shall be position the first R, and then factory shall equal to, for P in position R to the end, and then for each one for position and the limit. All right, position and the lim in zip this and the limbs and the position and limb. Then I'm going to print robots, print factory. Random choice takes 2 position. Wait, hold on. Choice takes 2 position. Choices. Lord. Choices. And then we need to say k equals. There we go. Hopefully one of these will fail. Relatively easy to deal with. Maybe I should. Oh, have a lot of error. Smaller. 5 robot, 3 factory. And good, we have 2 sets of test cases. Nice, good. Okay, let me save the test cases here. That's one set. Now we need another set. I would like to call it today. We'll handle this tomorrow. Let's see, where are the errors? Oh, lots of errors. 1, 2, 3, 4, 5, and 5th. 1, 2, 3, 4, 5. This one. Okay, that's where we can start our analysis tomorrow. Okay. Well, stop here. Yeah, we make progress.